My name is Dr. David Parsons, and I'm the director of the School of Meteorology here at the University of Oklahoma. A lot of my job is associated with running the school, but I also teach typically an Intro 2 class to undergraduates and a first year orientation class for students. So I grew up back east and did my undergraduate at Rutgers University back in New Jersey. I went to graduate school at the University of Washington in Seattle, working under Peter V. Hobbs, the well-known cloud physicist, the late Peter Hobbs. And I left the University of Washington and went to Boulder, and I spent over 25 years at Boulder, mostly at the National Center for Atmospheric Research, NCAR. At NCAR, I became increasingly involved in management. I ran an observing facility, was the manager there. It included LIDARs, profilers, scanning radars, airborne radars, as well as surface flux and in situ measurements. And while I was there, I got increasingly involved in international programs. Spent a year at Météo France as a visiting scientist in Toulouse, a summer at University of Reading, the Joint Center for Mesoscale Meteorology, there at Reading between the university and the UK Met Office, and then eventually got involved in a project called THORPEX. It was a UN project under the World Meteorological Organization. It was sponsored by 8 countries, and the idea was to accelerate improvements in the rate of improvement in numerical weather prediction, particularly for those high impact events that affect society. While I was at the UN system in Geneva, I got a call one day saying, please apply for the director at the University of Oklahoma. I came out and visited the school, saw the facilities, met with the students and faculty, and was instantly sold on that. And that was about 6.5 years ago. I have another 1.5 years to go as director. So when I came to the university about 6.5 years ago, we had an academic performance review, and it confirmed my thought that we were one of the world's leading programs for severe weather and related observations such as radar. But there was really a feeling in the review that we needed to broaden. We needed to have a seat at the table when it came to global circulations, atmospheric chemistry, climate variability. So our recent hires have been really pushing us in that direction for tropical meteorology, polar meteorology, Pacific predictability with ENSO, and also atmospheric chemistry. I think our goal right now is to continue broaden, but also to protect our strengths. So we've had 5 faculty retire in the past year, so we're in the process of trying to rebuild and redirect and protect our strength, but continue to broaden. Educationally, we've modified our graduate program quite a bit in recent years, and we really want to turn our attention to the undergraduate program. It seems that for undergraduates, if you stop at a bachelor's, then you really need a second skill, be it broadcasting with some intern experience, be it computer science, mixing in big data with meteorology, atmospheric chemistry, air pollution with meteorology, hydrology, etc. So we're really in the midst of revising our undergraduate curriculum so that students that aren't going to grad school leave here with a second skill and increases their employment options. About 35% of our students do go on to graduate school, and we've been quite proud of the academic and service awards won by both our graduate students and our undergraduate Blue Water Scholars, the Atmospheric Sciences First postgraduate Shelf Marshall Fellowship, NSF Fellowships, NCAR postdoctoral fellowships, etc. We have a great student body, and our goal is always to make the program just a little bit better. So the atmospheric sciences face grand challenges and opportunities in the next 5 to 10 years. One opportunity is the better communications of weather information, the better utilization of weather information. But there's also scientific challenges for the atmospheric sciences within our discipline. Our modeling ability to predict weather has generally improved about a day per decade, but there's been a big separation between those models that resolve or permit convective systems, storms to be directly resolved, and those global models and climate models where convection is parameterized as something happening within a large grid box. So for the first time now we're moving into an era where you can have global models at sufficiently high resolution where you actually are seeing storms actually directly modeled, but then you see the effects of these storms on the global circulation. For example, ENSO in California rainfall, or the treatment of convection over North America and forecast failures over Europe. These are problems that we've never really been able to look at in such a direct way. And it's kind of blurring the distinction between weather and climate, and it's opening up a whole new area. So I'd like to see the school move into these new areas, but also keep our strengths in weather and continue to broaden into polar meteorology, where we're experiencing some of the most rapid changes on the planet, help bridge the gap between weather and climate. And we've also been proposing a new initiative where we'd bring together civil engineering with air pollution and the chemistry department and our own department to look at more at the atmospheric chemistry, how constituents change, evolve in the atmosphere. And this ties into the new satellite award that happened by the Dean of the College, Berry and Moore, a $166 million award to look at carbon dioxide and surface processes from a geostationary satellite in space, a project called GeoCarb. I think probably my biggest piece of advice for students coming in is how you treat mathematics. Historically, there's been this way of thinking about math that, oh, this person's good at math, I'm not good at math. You know, this person's very good at math, oh, math is hard for me, or I don't like it. But to really master the atmospheric sciences, it involves a lot of mathematics. It involves a lot of physics. And I think my advice is to work hard at mathematics, work hard at the physics, the quantitative side, but don't be afraid to ask for help. Einstein was famous for this. He was a wonderful physicist, but he often asked for help with his mathematics. He was probably a better mathematician by far than I am, but he would go to people like Max Planck and colleagues also in the United Kingdom and say, I have this idea, and I can't quite get a mathematical handle on how to implement it. So I think when it comes to math, don't think of yourself as good or bad at math, but think of yourself as somebody, if you're going to be successful, you'll probably have to work hard at math at some point. And also, don't be afraid to ask for help when you need help on the mathematics. And sciences in general, it's a dialogue. So oftentimes you'll see somebody talking about a subject and something doesn't make sense or you don't understand it. Sometimes it's a gap in our knowledge and it leads to important discoveries. So I think work hard at mathematics, don't be afraid to ask questions, and also don't be afraid to ask questions about science in general, because that's how understanding is reached, and it also sometimes leads to wonderful discoveries. Research, since I've come to the School of Meteorology, has been fairly broad, involving several different subjects. One is polar research, focusing mainly on Antarctica. Another is convection. Right now it's convection over the Great Plains at night. And the third area is this idea of the interactions with global circulations leading to extreme events and leading to problems in numerical weather prediction that cause forecast bust. I'll return to the convection problem a bit. We've known for over 100 years, since 1916, that there's a maximum in convective activity in storms at night over the Great Plains. This makes the Great Plains somewhat unique, but scientists are still arguing as to why this nighttime maximum occurs. So we've been involved in both individual research and also was one of the leads for the Pecan project, Plains Elevated Convection at Night, to look at this problem. And then I'll also say a little bit about the rainfall and extremes. For example, we've been working now on processes over the Pacific, the interplay between the jet stream, between sea surface temperatures and how they vary with things like El Nino and ENSO, and how this leads to large-scale or leads to extreme events over the Americas. There's been a big thinking that, a lot of the predictive skill, say for rainfall in California, is really linked to El Nino. And the last two winters have really shown that not to be the case. There was an El Nino last winter, and Southern California was very dry, and this year it's very wet for a La Nina year. So we've been looking at that and finding that it's actually the nature of the jet streams over the Pacific, the so-called wave guides that carry the Rossby waves that cause our day-to-day weather, the highs and lows in mid-latitudes. The nature of these wave guides is very important because that determines where the energy from the convective systems go. So that's the topics that I've been working on. Right now I have 2 graduate students that I directly advise, both PhD students, a 3rd PhD student that I co-advise, and an undergraduate that is also working on the California Rainfall Project. And then there's 2 students that I advise, but this is a service to adjunct and affiliate faculty. We have a funny way of doing business. We meet one-on-one once a week as needed, but then the group gets together on Thursday night, and one person does a presentation on the research, and the person who did the presentation the week before is supposed to bring food for us all to eat while we listen to the next person in line present their results.